prove that that can be calculated with that. Dig it? To the whiteboards. All right, first thing we do is, as always, we prove a base case. Now, I'm not a fan of only proving one case in scenarios like this. When I have a weird scenario, like if I were to prove S of 1 to be true, what am I claiming? I'm claiming that the sum of 1 through 1 is 1. That's a little weird. Like when you use zeros, things get a little wonky, right? So if 0 is one of my things that's in my set that I'm using, I'll typically do 2 or 3 base cases, right? Theoretically, shouldn't have to do that, but it just makes me feel warm and fuzzy and safe at night. So I am going to prove it for 3 cases. You don't have to go that far, but I'm going to prove it. And how do we prove it? We just plug in 1 for n and calculate. We plug in 2 for n and we calculate. We plug in 3 and calculate, right? So if we plug those in, everybody see what I did there, right? We will find out that the sum of the numbers 1 through 1 is 1. That's what it'll calculate out to, and that is the correct answer also. If we sum 1 through 2, the formula will spit out 3, and we know that 1 plus 2 is 3. If we plug in 3, the formula will spit out 6, and we know that 1 plus 2 plus 3 is 6. So my base cases are satisfied. I'm happy with that. Okay. Once we do the base case, then we assume, sorry, I got all this extra junk in here. Once the base case is checked, then we're going to do our inductive hypothesis, which is we're going to plug in k. We're assuming that S of k is true. If S of k is true, then that statement is also true. Agreed? If S of k is true, that's true. We don't know if it's true, but we're assuming it to be true. Okay. So that's the P of our P, therefore Q. We now need to prove that this will also be true, right? This is 100% true without any proof. We know that it is true that S of k plus 1 is equal to 1 plus 2 plus 3 plus whatever, plus k plus 1. Do we buy that? That is a true statement regardless of k's value, regardless of any proof, regardless of our function. That is a true statement. You guys see why that's true? Let's plug in some numbers here. I'm getting enough blank stares that I want to plug in a few numbers to prove that. Okay? So I'm saying that P, do I have a P of S or no? That's an S of K. I'm saying that is equal to 1 plus 2 plus 3 plus 4 plus K plus K plus 1. Backwards parenthesis there. All right, in other words, if K were 7, I'm claiming, if K plus 1 were 7, I'm claiming that this is 1 plus 2 plus 3 plus 4 plus 5 plus my K plus 1 is 7, so what's K if my K plus 1 is 7? 6 plus 7. Whatever K's value is, that is a true statement, because the whole point is to sum up 1 through whatever number I'm talking about. Well, 1 through whatever number I'm talking about is, no matter what the numbers are, it's 1 through the last number, or 1 through 1 plus whatever, up to the next to the last number, plus the last number. Do you guys agree with that? Right? So in other words, the sum of 5 is equal to 1 plus 2 plus 3 plus 4 plus 5. The sum of 6, i.e. 5 plus 1, is equal to 1 plus 2 plus 3 plus 4 plus 6 minus 1 plus 6. Right? If this is just K plus, it's the number right before K plus 1. We don't know what that number is, but we know that K is the number right before K plus 1. Make sense? Or we say 5 plus 5 plus 1. That's all we're saying here. We get that? Good? Okay. So we know that to be true. Well, look closely at what's on the board there, and this can lead you down the path. Does anybody see there what's going on? Kind of hinted at it on that previous page as well. What is that? That is S of k. Is it not? Right? S of k is 1 plus 2 plus 3 all the way up to k. That's S of k. Well, we, air quotes, know that S of k is true, right? Therefore, I can replace that with what? K times k plus 1 divided by 2, right? Because we know, again, air quotes, because it's our hypothesis, that that's true. And we also know that that is the same thing as that, right? If I plugged in S of k, this is what I would get. And we also know that that is the same thing as that. Therefore, this and this are the same thing. Do you agree with that? Does anybody disagree with that or not understand why that's true? Let's go here. Look at this. If I have S of 3, would you agree that that is equal to 1 plus 2 plus 3?
Yes.
Okay. If I have, oh, hello, S of 6, would you agree that it's this? Yeah? Okay. Well, what if k happens to be the value 6? I don't know this, but what if it happens to be the value 6? Would you agree that that is true?
Yes.
Okay. Now, the catch is we never know what k is. So we just say it's 3 plus whatever plus k, because that might be 4, 5, 6, 7, 8, 9, 10, right? All the way up to who knows what number. Okay. Well, if this is true, would you agree that this is true? Going back to plugging in the value for k being 6, right? What's k plus 1? 7. So I'm saying S of 7, in other words, I'm saying this is S of 7 plus 7. Well, isn't 7 simply k plus 1? Or 6 plus 1? Right? Isn't that the same thing as putting a 7 there?
Mm-hmm.
So whatever k's value is, if this is true, if I add 1 to k's value, then this is true. You agree with that?
Yes.
All right, okay. So if that's true, well, what is that right there? It's exactly this right here. It's S of k. Agreed? Yeah? Okay. Well, so if we go back here, we now understand that this is that. Well, this is also that, because if I plug in k right here, I put a k right there, and a k right there, I will get this. Why is this true? How do I know that this is true? We assume it's true. We don't actually know. We assume it's true. Why? Because we're saying in the event that that's true, will k plus 1 also be true, right? Again, it goes back to this idea that proofs look like this. P, therefore Q. And whatever P is, if it rains, I will get wet. If it did not rain, I don't care about Q. I don't have any interest. If I win the lottery, I'll give you $1. If I didn't win the lottery, I don't care about Q, right? I don't care about it. So the only time I care what Q is if P happens to be true. So let's just take a scenario where P is true. And so we're going to assume that P is true. What's our P in this case? We're going to assume that that is true. If it is true, that must be true. Did I answer your question? All right. So we now know that that and that are equivalent. So I can substitute that in there. So that's what the next slide does, I believe. There we go. That is the same thing, and then we're going to bring down that k plus 1 there, okay? So everybody see how I got there? So back one slide. All I did was turn this into that, and then when the slide refreshes, this is going to go up to this spot right here, and you'll have that whole equation without this 1 plus 2 business. Okay. Like so. Okay. Now that we have that, remember what we're trying to do is, what are we trying to make that look like? We're trying to turn this into what? Yeah, this kind of format looking thing right here, right? All right. So what's something kind of obvious I could do with the right side of my equation there? I can, well, you say combine fractions. I only technically have one fraction. Yeah. Multiply k plus 1 by 1, or 2 over 2, which is 1, right? Which changes no values, but it gives us this, right? Agreed? Now, this is already starting to get a little bit closer to what we're looking for. I can add those two together, right? What does that look like? Just everything on the top over just the number 2, right? Basic algebra, okay? So now, what can I do? I can factor something. I could factor out a k plus 1, couldn't I? Right? So if I factor out a k plus 1, you'll end up with that. You can trust my math, but that is what you'll get. We're very, very close, right? What could I do with that equation there to make it look something like the purple box there? Is that the same thing? K plus 2 is the same as k plus 1 plus 1. You agree with that? Okay. Believe it or not, that's it. We're actually done. The question is, do you see it? I think that my next slide actually asks you that question. I put parentheses around there.
M equal to k plus 1. So we have M times.
We don't need to change anything.
Well, it's just saying you said, like, just so it makes it easier to say, we can say, like.
Okay,
M is
sure.
equal to K plus 1.
Yep, very good,
So
yeah.
then you replace k plus 1 with M.
Good observation, yeah. So what Daniel's saying is, I can let k plus 1 equal m, and so that would become an m, that would become an m, and what do I have? I've got some variable, plus 1 over 2, right? But we actually have, by rearranging what was known to be true, right? We didn't know if S of k was true, but we did know that S of k plus 1 will be the sum of 1 plus 2 plus 3 plus 4 plus ... plus k plus 1. We know that's true. And in the event that S of k is true, we know we could swap out all those numbers for the S of k value. A little bit of algebra later, and we end up with this scenario right here, which is exactly some number times, parentheses, some other number, the same exact number, plus 1 divided by 2, right here. So S of k does evaluate to this layout. Or sorry, S of k plus 1 does, in the event that k is true, that S of k is true. All right, what questions do you have about that? So there are more sample problems on this page, these pages in your book. I highly recommend you walk through them. It's important to understand this. Why do we care about this? Because this technique helps us prove the truth of an algorithm. If you write a recursive algorithm, which is a thing you'll do in the real world, and we're going to look at some of those probably today, but between today and next time we meet, we'll be looking at those. Okay, so you have, in order to prove a recursive algorithm to be true, mathematical induction is the way to go. You can also use mathematical induction to prove things like a bubble sort to be true, And I think we'll be able to look at those down the road a little bit when we get into, we might look at them next week, we'll see. But we will look at that in the future probably. Do we agree that this is solved? Maybe it's a little fuzzy still, but how do we feel overall? I want to make sure we have some sort of a clear idea of this, because we're going to switch gears and start talking about recursion here. And recursion is everybody's favorite subject, right? Nobody likes recursion. Recursion is the sad, neglected child of programming. All right. Any questions? We're moving on, phase 2 here. So let's look at some simple, looking at them mathematically first, and we'll look at them programmatically, all right? So here's how they are defined mathematically. You'll start off with your little f, and then that's supposed to represent a left curly brace. And remember, this is recursion, so what do you have to know when you're dealing with recursion? Yeah, you have to know a base case, right? At least one. Some functions you may need more than one base case, but we have one here. So we are just given that f of 0 equals 3. Who knows what this function does? Doesn't matter. Okay? But we are given that f of 0 equals 3. Now, here's where it gets weird. We also know that f of whatever n is at the moment plus 1 will be equal to 2 times f of n plus 3. With that, we can calculate f of any number. Okay? Recursively, but we can do it. So let's take a look at this using if I wanted to find what's f of 1, f of 2, f of 3, f of 4. We'll use a recursion table. First of all, do we understand the definition? You may not know what it's going to compute, but we see what it looks like. And then I'm going to show you how to actually plug in the numbers in just a second. Okay, we're being asked to find f of 1, 2, 3, and 4. So start off with the left side, which is going to be the numbers you're going to use to figure out, I want to figure out what f of 1 is, so I'm going to put, I already have 0, right? So we'll just put 0 there, and we know that it's 3. But now I want to figure out 1. What's f of 1? Well, how do I get f of 1? All right, so before we go down that path, sorry, I should clarify one little thing here. This gets a little confusing. This n here represents that number here, right? And that number here, and this number, and so forth, okay? In order to calculate this number, this n has to be something that's not this number, right? So how do I get f of 1 if all I know is how to calculate this? What does n have to be? It has to be 0, right? So what I'm talking about here, when I'm saying n here, I'm talking about figuring out what is the function f of 1 if I plugged in a 1 for the value right there. That's what I mean by this, okay? In order to calculate that, I'm actually going to have to look at n being 0 for the moment. So maybe I should have used a different letter here to make it less confusing, right? But how do I figure this out? Well, I plug in, I set n equal to 0, and then I say, what is f of 0 plus 1? Okay? Well, we know f of 0 plus 1 is going to be 2 times f of n. Well, what's f of n? It's 3, because n at the moment is 0. So f of 0 is 3. So it's 2 times 3 plus 3. What does that equal? Using order of operations, 9. Okay? All right, so looking at the next one, yeah, the answer to the next one is 21. So if we have 2, in order to calculate f of 2, then I have to have 1 plus 1. So at the moment, n is equal to 1, which is 2 times f of 1, which is 9. So that's 18 plus 3, which gives us 21. Now each time we do this, essentially it's going to be this number times 2 plus 3. That's what it's going to work out to be, okay? So that means that the next number should be 45, and the last one should be 93. Right? Feel okay about that idea, how to calculate something like that? Your homework is full of questions like this, tons of these, okay? All right, questions about that big picture. We're gonna look at some more examples in a minute. We feeling okay here? This is the Fibonacci sequence. With the Fibonacci, there are two base cases, f of 0 and f of 1, okay? And then the recursive portion of it is f of n is equal to f of n minus 1 plus f of n minus 2. We've seen that before. We know how that works. We looked at that when we talked about sequences, right? Here's another one. If you look at it, see if you can figure out what it is.
Is it the...
Yeah, it's a factorial function, right? What is factorial? What's factorial 5? What does that mean? 5 factorial, what does that mean? Yeah, it's 1 times 2 times 3 times 4 times 5. This is 1 times every number up to the number you're talking about, up to n, right? Okay, so factorial function. This is pretty easy to code too, right? You can look at this and write the code and just super easily, right? All right, so I just got the console open here. This is JavaScript, and we're gonna go right there to the console. And I can make a function call it factorial. We're gonna pass in some number n, and we have to first mention the base case. All right, so the base case is f of 1 equals 1, right? So if n equals 1, is there any other base case we have to think about? What are we going to return if n equals 1? 1. Is there any other time we want to return 1? 0. 0 factorial is actually 1. So or n equals 0. Then return 1. That's our base case. Else return factorial. Actually, it's going to be factorial n minus 1 times n. Or I think I use n, yeah. Factorial of n minus 1 times n. See that? That's it. Make sure I don't have any errors. Looks good to me. So let's do factorial 5. And we get 120. 1 times 2 times 3 times 4 times 5 is 120. Or do a smaller one we can see easily. Factorial 3 is 6. So when we look at this, if you can write the function out this way and see what it looks like mathematically, it's very easy to turn it into an actual method or a coding function, okay? So questions about that function there? To the whiteboards. I'm going to give you these problems here. We have given to us f of 0 equals 1. I want you to solve f of 1, f of 2, f of 3, f of 4 for each of those 4 equations on the left there. Okay? We know the first column, what the answer is for every one of them, right? It's 1 because it was given. So 1, 1, 1 all the way down. Looking around the board, I think everybody got the correct answers, so I probably won't spend too long walking through these. But if we plug in f of 1, we'll see that we should have 3, 3, 2, and 3. Everybody get that? Yep. Okay? And again, so every one of these, it's a scenario where we don't know how to solve for f of some solid number. It's always n plus something else. So if I want to solve for f of 1, I got to deal with where n is 0. So I get 0 plus 1, which gives me an f of 1, which will be equal to f of 0 plus 2, right? So f of 2, 5, 9, 14, 13, or 4, 13, I should say. Yeah, looks like everybody got that. Okay, good. 7, 27, 16, and 183. Nice. 9, 81, 65,000, and 33,000. Everybody got that? Looks like you guys know exactly what you're doing. You good? So any questions about that? I don't think there are because you guys nailed it. I think you're good. To the whiteboards. Now I noticed that two of the teams had the same answers for the first row that are different from one of the other teams. We'll find out in a minute who's right, or if none of you are, maybe. We know what f of 1 and 0 are already, right? Those are the two givens to us. So, one team has f of 2 for the first row as -5. The other two have it as -1. We think. Why is it -1? So we want to figure out what is f of 2, right? That's what we're looking at. Which means that n equals 1 at the moment. So, and that'll give us f of 2, right? So what is f of 1? It's 2, right? And then what is f of 1 minus 1? 0. So what's f of 0? -1. What's 3 times -1? -3 plus 2, -1. You guys missed the order of operations? Yep.
We inserted parentheses on our own.
Yeah, I can't do that. Yep. Follow the order of operations. That'll get you every time. Good. So that means that your whole first row is probably going to be off, but the rest of them looks like you got it right. So everybody follow the math on that? Okay. So let's take a look at the next number, -4 for f of 2 on row 2, 8 for row 3, and -1/2 for row for row 4. All right. Next up, 5, 32, 176, -4. So for f of 4, we get 2, -4096, 92,001/8. Good? So everybody got that for the most part? And then the last one, 17, 536,000, or million, excuse me, 536 million. And then 25 billion and -32. Good? Feeling all right? Okay. So lesson learned on this one, don't forget your order of operations. All right, questions about processing those. Again, your homework has a bunch of those. So we've started off the day by looking at mathematical induction. Mathematical induction is a proof type. There's sort of a recursive nature to that type of proof. Next thing is we looked at recursive functions, right? And now we're going to look at recursive algorithms. Now, everybody in this classroom should have been exposed to recursive algorithms. Doesn't mean that we all like them or can write them easily or understand them. They're tricky and they just take practice, okay? So let's just kind of review a couple things. Any method that calls itself is recursive, right? When you need to look at something in terms of another value being passed into the same function, that's recursion. Pretty much anything that you can do with a loop can be done with recursion and vice versa. So the question then, why use recursion? If it's so hard for us to wrap our heads around and you can use a loop instead, why use recursion?
It's cleaner.
Cleaner? Sometimes it is, very often it is cleaner. It's usually less code for one, usually a lot less code. And it's usually more efficient, but not always. And so one of the downsides, though, is it can be a little trickier to read, as we can see when we look at some, okay? So let's take a look at this. This is actually Java code here, and we have a class called Factorial, and in that class, it looks like I didn't make room for my closing curly brace on the class. Sorry about that. But on that class, we have our function called getFactorial, and then we also have the main function, the main method, okay? The factorial function is easy. If n is equal to 1, return 1. That's your base case. Otherwise, return whatever n is times, call myself recursively, n minus 1, okay? This main method right here is going to call the getFactorial method on the number 5. So how do you figure out what the output's gonna be? I mean, we know it's called get factorial, so we know it's gonna be whatever 5 times 4 times 3 times 2 times 1 is, right? We know that. But you can actually use either a recursion table or a recursion tree to see how these work. So let's start with the recursion table, which we have talked about already when we were looking at the regular mathematical functions. Also, keep in mind the rules here. You always have to have a base case. If you don't have a base case, you'll never get out of the recursion, and you'll have infinite recursion, which is far worse than an infinite loop, okay? Then make sure that the else, which is the non-base case, right? So you have your recursive, your base case right here, and then your else statement is the recursive case. And very important, make sure that the else case will eventually reach the base case. Otherwise, infinite recursion. So let's start off here. I want to figure out what get factorial 5 is. If I didn't know what that calculation was, I didn't know how to calculate it manually, I want to walk through this function. Here's how you do it. Start off again with the knowns. And by looking at the function, what do we know?
1.
Yeah, if n equals 1, it returns a 1. Now, notice my space between the parentheses, the equal signs there. That was just so you can see that it's a double equal, because it seems like they blended together a little too much without doing that. All right, so we know that the input of 1 will give us the output of 1 as well. Okay, that's good. What is the input of 2 going to give us? Well, here's what happens. It asks the question, is n equal to 1? No. Then return n, which is what? Nope. N is 2, times get factorial 1. Right? What's get factorial 1? 1. So it's going to return 2 times 1, which is 2. Plug in the number 3, and it's going to, again, it's going to say it's not equal to 1, so it's going to return 3, which is n, times get factorial 2, and you'll get 6. Do it again, plug in 4, and you're going to get 4 times 6, gives you 24. Plug in 5, you get 5 times 24, and you get 120. Okay? But that, using a table like that, you can see what output a recursive function will do. You can also use a recursion tree, which I kind of like a recursion tree better. Okay, so we're going to cover this, and then we'll stop, and then next time we meet, we will go through some examples in teams on the whiteboard where you guys walk through some functions that you don't know what they're going to do by using these techniques, all right? So you start off, I've changed it, notice here, to get factorial 4, right? Not 5, because I ran out of room on the screen. But what do we know about get factorial 4? So what's going to happen if I pass a 4 in here? It's going to run that line of code, right? So what is that line of code saying? It's saying 4 times get factorial 3, right? So in other words, get factorial 4 is the same thing as 4 times get factorial 3. Do you agree with that? How do I know that? Well, because it says so right here, right? 4 times get factorial 3. Well, that being the case, we also know that get factorial 3 is 3 times get factorial 2, and then 2 is factorial 2 is get factorial 2 times 1. What's 1? Our base case, right? Get factorial 1 is our base case. So we know the number. That's given to us in the function. That's 1. So now we know that's 2 times 1, which equals 2. Which means if that's equal to 2, then that's equal to 2. Right? Well, now we know 3 times 2 is equal to 6, which means that's equal to 6. And we know 4 times 6 is 24, which means that's equal to 24. Make sense? Okay, if there are no questions, we'll pick up this discussion next week.